Welcome. Today's notes worksheet is entitled Tangent to a Curve. This lesson represents a transition for us in our little unit on calculus. We will be utilizing the concept of limits as we develop some pretty powerful ideas on how a function changes. So we'll actually be talking a lot about slope today. I do have a big space for us to go ahead and put a graph in place and then kind of talk about a couple ideas. So please take good notes with this. There's some things to develop as we go through, and we'll see if we can do that to the best of our ability. So let's go ahead and give it a try. There's this spot for a graph, and I guess what I'd ask us to do is get a coordinate plane going. And let's go pretty top-heavy in the first quadrant there, just a little easier for us to do. And then, I don't care, it doesn't make a difference to me, but let's go ahead and draw some type of graph that'll pass the vertical line test, so it's a function. I just have a parabola going. I'll probably utilize a parabola a couple times over the course of this lesson. And then we're going to do some labeling on this. So this is a very particular diagram that talks about how a function changes. And so let's go ahead and start this off here. I guess the first order of business, everybody, is to go ahead and find a point on the graph of your function. So if you can do that for me, that would be great. And let's go ahead and talk about the input and output here. I'm going to label this with an ordered pair. And so the input I'm going to call x, and I'll represent that graphically in just a second. And then the output, of course, instead of y, I'm going to call it f of x. So we have x and f of x representing our initial point right there. And again, what I'm going to do is relate that to the horizontal component. So everyone, if you would, drop that on down to the x-axis for me. And then bring it on over to the y-axis. That would be ideal. And then I think we can all be safe in our assumption that from the origin to here, that would be x. So I'm going to put a little x just right there. And then, of course, from the origin up to here, that would be the y, or the function value at x. So something like that would do. Okay, so what I need you to do is get that point in place. And then what we're going to do is create a secondary point. And I'm going to do that just out here, if you can kind of spot that on your screen. And if you can go ahead and put a point out here, that would be fine. And before I label, in this case, I'm going to go ahead and drop it to the horizontal. So bring that on down right there. Excuse me, and then bring that over to the vertical, something like that right over there. So what we need to do is label that second point, and that is done in a very particular way. But before we do that, we have to talk about one very important quantity that comes up in calculus here. And that would be, if you can kind of see your screen here, the horizontal distance from this first point to the second point. So right in here, if you can spot that, that's what I want to focus on here. And we'll actually focus a lot of our attention on this quantity today during this lesson. So from here to here, the horizontal distance from the first point to the second point. Now some textbooks will call that the change in x, or what's called a delta x. But most textbooks actually call it h. And so if you can go ahead and relay that piece right there, from here to here is going to be our h value. And again, that's the horizontal distance from the first point to the second point. Now I think that allows us to go ahead and label a couple things appropriately. The full horizontal distance from here to here, and then I guess the full vertical distance from here to here. Basically what we need, everyone, is our second ordered pair. So I'm going to get that ready to go, and let's go ahead and label that piece. And I guess I would ask you this. How far now is it from here all the way to that second point? How would you label that? Well, from here to here, I think we all agreed that was x. And now from here to here, I labeled that h. And so from here all the way over, I'm hoping that you would see x plus h would be the appropriate expression for that. Okay, so we have an input now of what we would call x plus h, x plus the h value to get from here to here. So I'm going to go ahead and label that down here as well. And now, of course, the output, very simply, is the function value at x plus h. And so f of x plus h. And let's go ahead and put that in its appropriate spot as well, all over your diagram. Okay, now I hope everyone's okay with that piece right there. And what we're going to do is talk about the slope of what we would call the secant line. So a secant line is a line that goes through 2 points on the curve. And as you can see here, I have one point right here, a second point right here, and what I'm going to do, everybody, is draw a line going through both of those points, something like that. I think I got it through for the most part there. And then I guess I would ask you, could you now go ahead and tell me what the slope would be based on the quantities that I've labeled for each point? So remember slope, first and foremost. Slope is y2 minus y1 over x2 minus x1. And so use this point, this will be your second point. Use this point, this will be your first. And could you come up with the slope of the secant line? All right, well, maybe let's see how you did here. So y2 minus y1, everyone. So I would do f of x plus h, that's y2, minus f of x, so the function value at x. There's y2 minus y1, and then over, of course. And what we would do now is x2, there it is, minus x1. So let's play that in. x2, so x plus h, minus, and then x right there. Hopefully everybody kind of sees that piece. Just slope, guys. Don't overthink this piece because it is just a fancy way to talk about slope according to my particular diagram. And now you can see, of course, this top, not much I can do there, but look at the bottom, everybody. I have x plus h minus x. What happens to those x's? Well, they cancel out. And so, long story short here, I'm going to have to come right over here. Hopefully you can find a little more room. But I have f of x plus h minus f of x, and everybody, all of that is over h. Okay, box that up for me if you would. And that is the slope of the secant line according to my diagram. I hope everybody has that piece. Now, this is a very static diagram, basically. It's just a drawing on the board. You see it on your screen. You've drawn it now on your paper. What I need us to do is start thinking dynamically with this diagram, meaning what we need to do is kind of see this in action. So to the best of your ability, let's kind of just look at this piece, and then I have a program that will hopefully illustrate it even better. But now what we're going to do is play around with that second point. So just watch up here really closely if you could. You don't have to write anything down. But basically what I'm going to do at this stage, everybody, is move the second point. And so picture it, guys. I'm going to move that second point. Does everyone kind of see that? Moving it, moving it, moving it. And I hope everybody would agree, as I move the second point, the slope of the secant line would change, right? Of course, that second point is changing, and so the slope between the 2 points is going to change. All right, now I'm moving it, and as I move that second point in, is everyone comfortable with the fact that h is starting to get smaller and smaller, right? So as I move this second point in, see it, guys, see it. As I move that in, do you see that this h, this quantity, this horizontal distance between the 2 points is getting smaller and smaller and smaller? All right, so now let's go further with it. It's moving in. It's moving in. It's doing great. Again, the slope of that secant line is constantly changing as that second point is moving, and it's moving closer and closer and closer. What happens as that second point starts to get really super close to that first point? Well, guys, it's still a secant line, right? Because it's going through 2 points. It's going through 2 points. But as it gets closer and closer and closer to the first point, what we start to do is transition. We can start thinking of not the slope between 2 points on the graph of the function, but literally, as this gets closer and closer and closer, we're going to start talking about the slope at 1 point on the graph of the function. Okay, I'm hoping everybody sees that piece. So let's go ahead and write just a conclusion in place, and then we'll go ahead and see this in action. So it says, conclusion 1, as x plus h gets closer and closer to x, so the second point getting closer and closer to the first point, or as I specified, everyone, as h is getting closer to 0. Here's what I wrote. The secant line, and that's what we were talking about, the slope of the secant line. The secant line gets closer and closer to what I guess we would call a tangent line. All right, so I hope everyone is comfortable with that premise right there, that as that second point moves in, we start to look at not what happens between 2 points on the graph of the function, but literally what happens at 1 point on the graph of a function. Now, again, let me bring up my program, drop those pencils for just a sec, and maybe, just maybe, we can kind of see this. So I just use my sketchpad here to create a function, and just random here, of course. I've got 1 point right here, and I have a second point right here. Hope everybody sees that. Notice, guys, there's a secant line going right on through those 2 points. That's great. And now let's see if we can kind of track this. I'm going to try to bring this in as best as I can. Notice, as that second point moves in, obviously the secant line is changing, so its slope is changing. Again, it's still a secant line, no doubt about it. Here it comes, guys, and notice the horizontal distance between the 2 points is getting smaller and smaller and smaller, right? So h is getting smaller and smaller and smaller. Everyone okay with that idea? So as the second point moves closer, h is getting smaller and smaller and smaller. And notice what's happening here as we get closer and closer. Can I start to see that we're beginning the transition from the slope of a secant line to eventually, as this point gets infinitely close to that first point, do you see that we can now start talking about the slope of a tangent line, what's going on at a single point on the graph of the function. Everyone okay with that? So here we go, one more time, just so you can kind of see that transition. And as it gets infinitely close, we can start to talk about the slope not of the secant line, but of the tangent line. Well, pretty awesome. Okay, let me bring back my screen, and let's go get some more stuff here. So the best thing for us to do is just to start with a very particular graph, and then see if we can go ahead and calculate the slope of our secant line based on what we have, and then kind of move forward from there. So everyone, example 1 on your paper, let's see it. It says, investigate the graph of y equals x squared. Perfect. Probably a nice, easy function to do this with. And guys, if you get a chance, give me a coordinate plane if you would. And here's what I'm going to ask you to do. Just give me the graph of y equals x squared. Looks something like that. No tick marks necessary. And, you know, I'm going to just do this for the time being. It really doesn't matter where we are, but I'm just going to call this my first point, x and f of x. And then I'm just going to come out here and just call this my second point. That'll be our x plus h and f of x plus h. Just totally arbitrary here. And obviously, you know, any 2 points on the graph of the function, I can find the slope, and that's exactly what I'm going to do. So what we're going to do is use that formula from above. And you did this first semester, as a matter of fact. We kind of called it by a different name. Not sure if you remember the phrase difference quotient, but that's pretty much what happened here. And so here's what we have at this stage. The slope of the secant line at this point is this, f of x plus h minus f of x all over h. And so now that we have a particular function, and by the way, everyone, wouldn't be a bad idea for our purposes here. Let's go ahead and talk about how our function is defined. So f of x is equal to basically just x squared, the input squared. And you have seen this before, so let's see if we can run through the idea. So this is an expression where we have the top left that talks about f of x plus h, meaning we want the function value with an input of x plus h. Really, the long story short, guys, is we're just going to take x plus h and use that as our input. We're going to replace all the x's with x plus h. And so what I'm going to do here, guys, is just take that x and replace it with x plus h. So instead of x squared, hey guys, it's just x plus h squared. Everyone okay with that premise? All right, now minus. Then we go on back and we say, all right, let's take our function and put x back in. So here's my function, I put x back in, and of course, just x squared. In the past, guys, I've put that in parentheses, and I will probably continue to do that, by the way. And then all of that is over h. So again, what we're doing basically is evaluating what's called the difference quotient for this particular function right here. All right, and that difference quotient should be the slope of the secant line for our 2 points the way they're labeled. Okay, everyone, let's clean this up. Now, guys, you would FOIL this out. This is x plus h times x plus h. You'll be doing this a lot, so kind of get used to it. If you FOIL it out, you get an x squared. You get 2 xh's, one from the outside, one from the inside. And you get the last, give me h squared. Then I can remove the parentheses and just do minus x squared. You'll see a lot of good things happen algebraically with this. What happens to the x squared? You have a positive and a negative. They cancel out. Now just be a little careful with your math right here. It looks like I have this stuff remaining. And there is something I can do algebraically to simplify that. And I'm going to go ahead and do that. Actually, I'm going to have to bring this up here. So at this stage, I have 2xh plus h squared, and that's over h, of course. Okay, now, good algebra, that's what this comes down to. Always looking to simplify things, and I see that that top factors by taking out an h. And if you take out an h, you end up getting that piece right there, and the h's would cancel. One on top, one on bottom. As common factors they go. And lo and behold, guys, let's write it right here. So the slope of our secant line for this function is, and let's get that in place, 2x plus h. All right, I'm going to box that up because that's looking great. So at this juncture, I should be able to give you any function, and you can come up with what we would call the slope of the secant line. And in this case, it's 2x plus h. So if I had an x value and if I had an h value, then I could go ahead and get the slope between any 2 points on the graph of this function. Everyone okay with that description? Okay. Now let's go ahead and get specific with this. And let's go to my next board, and let's see what we want. So it says, now let's look at what happens at a particular x value. In this case, guys, I'm going to go with an x value of 1 as h gets closer and closer to 0. So, guys, I'm going to get dynamic with this. I'm going to make my second point get closer and closer to the first point. So let's go back to the diagram just 1 second. Sorry for having you flip over here. But I'm going to give you a particular x value. I'm going to give you an x value of 1, just my choice. And so x value is 1. And by the way, what would be the y value on this particular function? Well, 1 squared is 1. So there it is, 1 comma 1. So now I'm going to go from this point to a second point. And what I'm going to do, guys, is bring that second point. Maybe I'll start it out here first. Then I'm going to bring it in. Then I'm going to bring it in. Then I'm going to bring it in closer and closer and closer. Okay, and what I want to do is see what happens to the slope of that secant line as the second point gets closer and closer to the first point. I hope that makes pretty good sense. All right, excellent. So guys, here's what this table is going to look like, by the way. I have 1, 2, 3, 4, 5, 6, I think it's 7 that we're going to do. So be ready. You're going to calculate with me. These calculations should be nice and straightforward. So 2, 4, 6, and I think I've got the 7. There we go. And so now, guys, what I'm going to do is talk about that h value. Remember, the h value is the horizontal distance between the first point and the second point. And so I'm just going to pick a number. I'm going to start it out relatively small. I'm going to let h be 2. Okay, and based on those two things, and by the way, I'm going to have to get my answer from the front side up here. Remember, slope of the secant line is 2x plus h. So we have that piece right there. If I have x and I have h, can I pretty easily go ahead and get the slope of the secant line? Oh, yeah, of course. So let's do it here. And I'll show this to you and how that plays out on the graph of the function momentarily. But let's do some nice, easy calculations. So guys, x is 1. That's going to stay fixed at this point in time. H is 2, meaning the second point is 2 horizontal units away from the first point. Alrighty, so 2 times 1 is 2, plus 2 is 4. So the slope of the secant line when h is 2 is 4. Now humor me one more time just so I can show you exactly what that would look like right here, and then we'll go ahead and just do the calculations the rest of the way. Now what that would be, and you don't have to write this on your paper. In fact, don't. Just kind of peek it up here if you can. But basically, I'll just put the point right here. If h is 2, that would be from here to here. That would be 2 units from there to there. This is our h, essentially, right? From here to here. And if h is 2, that means that this point right here would be 3, right? Because 1 plus 2 would give me an x value of 3. And of course, guys, 3 squared happens to be 9. So if h was 2 from here to here, that means we would be going from 1, 1 to 3, 9. And guys, if I asked you to find the slope right here, you would do y2 minus y1 over x2 minus x1, right? Hey guys, 9 minus 1 is 8. 3 minus 1 is 2. 8 divided by 2 is 4. And if you take a look at our answer right there, that's why I love all this coming together. Look at that. That's what that indicated, that the slope was 4. Now again, what I could do is for any particular value, and that's what I'm going to do right here. So guys, now we're going to let h get closer and closer to 0. Here we go, guys. So what if h is 1.5? Now we're going to bring that second point in. Keep it easy, guys. Keep it nice and easy. 2 times 1 is 2. 2 plus 1.5, so x and h, and should be 3.5, right? All right, so now the slope is 3.5. How about if h is 1? That would be only 1 unit away from the first point. Ready? 2 times 1 plus 1. 2 times 1 plus 1 is 3. Excellent. Let's keep going. Here we go. Now even closer. Now what if h is only half a unit away? Well, guys, 2 times 1 is 2, plus 0.5, 2.5. All right, let's keep going. Here we go. How about 0.1? What if the second point is only 1/10 of a unit away? Awesome. It's getting close. Well, 2 times 1 plus 0.1. And I'm hoping you see it's 2.1. All right, just a couple more here. What if I was only 1/100th of a unit away? What if h is just 0.01? Excuse me. All right, same deal, guys. 2 times 1 plus 0.01. That's it. There's your slope between the 2 points. What if h was 0.001, 1/1000th of a unit away? What would be the slope of the line between the 2 points? And you could see, hopefully, at this stage, that would be the slope. Hey guys, could I keep going theoretically? Could I do a little ... on this? And could I get h to be closer and closer and closer to 0? And could I start to see what's going on with the slope here? Doesn't it seem like it's getting closer and closer to a particular value? Yeah, and that's our conclusion. So let's read conclusion number 2, and let's pull this off. All right, so guys, as x plus h gets closer to x, meaning very simply, the second point is getting closer and closer to the first point, or, again, another way to think about that, h is getting closer and closer to 0. The slope of this secant line seems to be getting closer and closer numerically. Look where it went from 4 to 3.5 to 3, 2.5, 2.1, 2.01, 2.001. Could you understand what's going to happen again and again and again? It seems like the slope is getting closer and closer to 2. Does everyone see that? Awesome. Okay. Well, here's the issue. At this stage, and wait just a second before writing on it, we came up with the slope of the secant line as this. Right? There's the slope of the secant line. Now watch this. This is what's kind of fascinating about this piece. What we want to do now is transition from the slope of the secant line to the slope of the tangent line. And so remember what we kind of said there when we transition, everybody. Let me just see if I can get to it real fast. When we transition from the slope of a secant line to the slope of the tangent line, h is getting closer and closer and closer to what, everybody? 0. Now take a look at that expression. What's kind of fascinating about it? Officially, guys, if you look at this expression, can h actually ever be the number 0? No, because that would make me divide by 0. So I have a dilemma here. I want to find the slope at one particular point. I want to find the slope of the tangent line. In order to do that, h needs to be 0. And according to this expression, that seems like that's not going to work. So we need to find a way around that. And here's how we do it. We take the limit as h is going to 0. And I've been pretty much alluding to this idea for the past 5 minutes or so. Notice what we've been doing in this case with the table, right? I've been looking at what happens as h gets closer and closer and closer to 0. And again, theoretically, I could keep going here, 0.0001, et cetera, et cetera. I can keep going and going and going. And by doing this through this table, I can start to see what's going on with the slope of this line, that it's getting closer and closer to 2. So I can then make a conclusion just like this, that the slope of the tangent line when x is 1 is 2. Pretty crazy, huh? All right. So I take the limit as h goes to 0. Awesome. So, guys, let's do this. Remember the slope of the secant line for the last problem? So let's go back and take a look. Here it is. Remember that was the slope of the secant line, right? Now take a look. What do I want h to do? I want h to get closer and closer to 0. And remember our limit properties. If I can put 0 in for h. And so by putting 0 in for h right here, what do I end up getting? I end up getting just 2x. So h goes to 0, and when h goes to 0, I end up getting just 2x. So what's kind of fascinating about this is now we can start talking about the slope of not the secant line, but the tangent line at any single point on the graph of a function, which is quite powerful mathematically. So look how easy this is once we do this. Once I have this, we're ready to roll. So let's see, when x is 1, right? 2 times 1 is 2. And isn't that what we came up with in our conclusion right back here? Sorry for going back and forth. Isn't that what we came up with? When x is 1, it looks like the slope is getting closer and closer to 2. And so the slope of the tangent line is 2. How about when x is 2? Again, look how easy this calculation is. You can't get much easier. 2 times 2 is 4. How about when x is negative 1? 2 times negative 1 is negative 2. How about when x is 0? 2 times 0 is 0. Could I theoretically come up with a slope of the tangent line at any single point, the infinite number of points on the graph of the function, just by plugging it into this expression right here? You bet. Hey, let's just check those answers really fast, and then we'll begin to wrap this up. So, by the way, and let's see if I can do this with some justice here. It's not going to be perfect, but that's all right. So the first one was when x is 1, right? Here's the tangent line right there. Take a look at that. Does that look like theoretically the slope is 2? Yeah, I mean, it's an inclining line. Slope happens to be 2 right there. I think I had one where x is 2, right? So again, don't write this on your paper. Just peek. So here's the slope of the tangent line when x is 2. I saw that we got an answer of 4. Notice that's a little steeper than this one right here. Slope of the tangent line is 4. I think I saw something when x was negative 1. So here's what the tangent line, let me see if I can get that a little better. There's the slope of the tangent line. Does that look like it would be negative 2? Yeah, it's a declining line. How about the last one I think I saw there when x was 0? That would be this. And as a matter of fact, the tangent line for that particular point would be perfectly horizontal, just like that. There's the tangent line right there. And guys, what is the slope of a perfectly horizontal line? 0. And again, could I do that for any of the infinite number of points on the graph of this function? You bet. Of course I can. Awesome. All right, let me see where I'm at on my notes worksheet here. And there we go. That's looking great. Let's just put a couple things in place. So put an asterisk next to this one. So when we talk about the slope of the tangent line, we're going to talk about it really using two different phrases. So the slope of the tangent line is what we would call the derivative of a function. So you'll notice the next notes worksheet happens to be entitled Derivatives. All right, good. So the slope of the tangent line represents the derivative of a function, or, and here's the powerful thing in terms of applying it, not what happens between 2 points, but really what happens at a single point. So we would call this the instantaneous rate of change. Hey guys, slope is all about rate of change. And when we talk about, in this case, the tangent line, we're talking about the rate of change at a single point. It's instantaneous rate of change. And that's what's pretty powerful about it. Obviously, anytime you've ever talked about slope, it's between 2 points. In this case, it's not. It's at a single point. Okay. So guys, let's just wrap it up with one more, and I think this is great. So example 2 says, find the derivative of this quadratic function right here, then find the slope of the tangent line at a particular point. Okay. You guys ready? One piece of notation I did not put in, and I think I'll have to go back and put that in just a little bit, but the derivative of a function has some notation that goes with it. It's what we would call f prime of x. So if you could for me, put in a little f prime of x just like that. And basically now it's the limit as h goes to 0. So here's our key, guys. It's the limit as h goes to 0, as we saw from our previous screen, of that nice expression that we've actually had some experience with. The only added layer to what we've seen before is now we're taking the limit as h goes to 0. Okay, so let's do that. So if you remember, it's the limit as h goes to 0 of f of x plus h. So guys, take your function, and very simply, all you have to do is replace all the x's with x plus h. So here's my function right here. I'm going to replace all the x's with x plus h. So replace them. Okay, good. Then the minus. Everybody give me a minus right there. And in the top right of our expression says, you know what? Go back in and put x back into the function. And all of that, guys, is over h. Now remember our properties with limits. This is why this is a great transition lesson for us. We want to put h in, don't we? I'm sorry, we want to put 0 in. But can I put 0 in at this stage? No. So I have to wait and wait and wait until I can. So guys, let's go clean this up. I know you can pull this off. Again, you'll do a lot of this foiling, x plus h squared, so be ready for it. If I FOIL that out, I get x squared, I get 2xh's, I get h squared. Now clean it all out here, guys. Remove those parentheses. Minus 4x, minus 4h, plus 1, and then remove the parentheses on the back with that minus, minus x squared, plus 4x, minus 1, over h. Now it looks ugly, doesn't it? But don't panic. Good things are going to happen here. So if we've played our cards right, and it looks like I have up here, the x squareds cancel. 1 positive, 1 negative. The 4x's cancel. 1 negative, 1 positive. And the 1's cancel. Positive and negative. And so I'm going to keep writing things. If you can shortchange this a little bit, you're more than welcome to. But notice what we have. The 2xh is still there. The h squared is there. The minus 4h is there. All over h. Now again, my property is I want to put 0 in for h. I really do. Am I allowed to do that algebraically at this stage? No. I can't put 0 in for h. That would be major mathematical trouble. So I need to keep going with this. And guys, look at the top. Do you see that we're going to factor out an h from the top? So let's do that. It's just good math. That's all. So we keep taking the limit as h going to 0. Keep writing it. And now I pull out the h. And I get 2x plus h minus 4 all over h. Oh, this looks great because what's going to happen, everybody? H's, they're gone. And so I get the limit as h goes to 0 of 2x plus h and minus 4. Does everyone see that piece? And so when all is said and done, here's what we do. Last step, guys, I know you can pull this off, so really pay attention to this piece. I want to put 0 in for h. Here I couldn't do it, here I couldn't do it, here I couldn't do it, here I can't do it, but now, guys, look, can I put 0 in for h? Yeah. And so that's what I want to see happening. So it transitions from the secant line to a tangent line by making h go to 0. And when h goes to 0, I literally take that 0 and put it in, and I get just the 2x minus the 4. When the h goes to 0, I see what happens. And this is basically what we would call the derivative of the function. And there it is, guys. Please write that in there. That is the derivative of our function. All right, let's put that in place. Now remember what this gives me. This gives me the slope of the tangent line for any point on the graph of the function. So if I have a point on the graph of the function, can I use it? Yeah. So let's just do this last piece. Literally takes just a second. This is just one point amongst the infinite number of points on the graph of this function, right? Just one single point. Could I find the slope of the tangent line at this one point right here? You bet. All I need is that x value. The x is 2. So in this case, I'm going to write it like this. Slope of the tangent line. I'm going to write at 2, negative 3. This is not ideal, by the way, but that's all right. So the slope of the tangent line, very simply, is just 2 times 2 minus 4. I just put in the x value in for here. And 2 times 2 minus 4 happens to be 0. And so the slope is 0. And that's it. Could I do that for any point on the graph of the function? Yeah, absolutely. All right, guys, a lot to kind of process there. I totally understand that. The good news is the next notes worksheet is really just review, nothing more. But I hope the concept is working for you. Hey, thanks for listening. And please, guys, ask questions. And remember, this is sort of the beginnings of college-level calculus, so it's not easy by any means. But I know you have the capabilities to handle it. So let me know if I can elaborate on anything. Thanks for listening.